Okay, so today let us start about the basic discussion on black holes. Right, now you see this word, basically this black hole, it took a long time to emerge, you see, this story of black holes, it basically begins with the birth of general relativity and the Schwarzschild solution, and both of these, that they have been published in the year 1916. However, long before that, in the context of this Newtonian gravitation, there has always been speculations regarding dark stars, and this is what people used to say pre-general relativity era. People used to call them dark stars. That means material objects so dense. So pre-1916 we used to have dark stars, something like this, in the Newtonian gravitation, right? So basically we used to have what are dark stars? Basically material bodies so dense that light would be unable to escape from them. Now what's the thinking? The thinking behind this proposal is very simple. Suppose we have a projectile of mass m, projectile mass small m, and this is launched from the surface of a spherical body of mass capital M, right, and radius capital R. Now then, in order to escape from the gravitational influence of the body, then the projectile, so to escape from the gravitational influence of this body, the projectile must gain gravitational potential energy. So projectile must gain gravitational potential energy. And what's the energy? It is just basically gmm by r. Now if this energy is to come from the projectile's initial kinetic energy at the time of launch, then the required launch speed is basically what? The escape velocity. And we just write like this. So we write half mv escape whole square is equal to this. And from this expression, basically we get the expression for escape velocity equal to root over 2gm by r. Fine. Now you see that this escape velocity will be greater than the speed of light c if the radius and mass of the body are related by what? So this escape velocity must be less than the speed of light. Now I am talking this in a different way. So I am talking it like this. If escape velocity will be greater than the speed of light, like this, if r is less than 2gm by c square, and such a body basically, so such a body what would trap light. Now we are talking about something light, something whose rest mass is 0. So if it can trap light, what about us? Okay, of course we will be trapped, and therefore so the body would be dark, right? Now do you know when these ideas were introduced? These ideas were introduced by John Michel and Laplace in around 17 to 1800. These ideas were introduced by John Michel and Laplace, okay, basically in the 18th century. Now these ideas that we are discussing right now, using the basics of escape velocity, they have got very little to do with the black holes of general relativity, but they do show that the physical concept of gravitational light trapping is not new. Now you see the idea implicit in the Schwarzschild solution is that, and this was developed in the year 1915, and though that it was not the properly associated at that time. You see, let me write down the Schwarzschild solution. So Schwarzschild metric, let me write it down. So it took some years to really understand the significance. dr square divided by 1 minus 2 gm by c square r, again minus r square d theta square minus r square sine square theta d phi square. Okay, now you see, this was basically the Schwarzschild solution. Right, now let's see what's the importance of this. Now you see, the Schwarzschild radius of real bodies, say 3 km for a body of the mass of the sun, is thought to be so small to be of any physical significance. So its physical nature did not receive much attention at that time. Now let me tell you a little bit about the history, what happened at that time. Okay, so I am going to talk about how we really discuss about the physics of black hole in general relativity. How do you define this and how this all came into existence? You see, it was pointed out after the Schwarzschild solution in 1915. It was pointed out during the 1920s that not, let me write it down, not all singularities in the metric g mu nu are physically significant. Now, so what will happen? Then this means that there would be a consequence of the coordinates being used rather than physics being described. And this opened up the possibility that bodies might be able to undergo a complete gravitational collapse. Now let me talk about this. Why are we saying this? Now look into this metric. Does it look perfectly fine to you? At first instance, it looks fine. But look over here. What will happen when this 2 gm by c square r is equal to 1? What will happen? Then this term will just blow up, right? This term will just blow up. Similarly, there is another problem. What will happen at r tending to 0? Again, this term will blow up. So basically, if you see very clearly, then this metric has got, in a way, two singularities. Now, let me, without going into the mathematics, this you will learn in your 4th semester, that out of these, one is an essential or gravitational singularity, and that you can never remove, and that is always inherent in the system. That is known as gravitational singularity or essential singularity, and that is r tending to 0. This one, this is an gravitational or essential singularity over here, right? Now there is another singularity, and that is when this happens, and that is at r is equal to rs, Schwarzschild radius. And you see, this singularity is basically because of the use of the coordinates. It's not due to physics itself. Okay, and so if we use the different coordinates, we can get rid of this singularity in this metric over here, if we write this in terms of a different coordinate. Right, so so as I was saying, the basic fact that people realize that this not all the singularities in this metric g mu nu are physically significant, this opened up the possibility. So possibility, the that bodies might be able to undergo a complete gravitational collapse. Gravitational collapse. And shrinking to a point of infinite density, irrespective of any surfaces that got in their way, provided that those singularities were entirely due to the choice of the coordinates. Now you see, in the case of a spherically symmetric body surrounded by a empty space described by the Schwarzschild metric, the singularity associated with R is equal to Rs, this one, you see, it was essentially recognized as coordinate singularity. But this knowledge was quite slow to spread, and the belief that the singularity was physical, it remained common at least until late 1930s. Now, in any case, planets were not sufficiently dense to undergo a complete gravitational collapse. Why? You see, the electrical repulsion between the atoms that they contained was sufficient to balance the gravitational tendency to collapse. Now, what about normal stars? Well, again, normal stars such as Sun were also resistant to gravitational collapse. Now, you see, the plasma at the center of the Sun is believed to be roughly 10 times denser than lead. But even at these densities, the thermal pressure resulting from the energy releasing the nuclear reactions is sufficient to guarantee a star's equilibrium. So basically I am talking about the hydrostatic equilibrium, right? So stars having normal hydrostatic equilibrium, they won't do the gravitational collapse. Planets, where the electromagnetic force comes into the play, they won't collapse. Okay. Now, you see, the astrophysics of highly evolved stellar bodies in which the nuclear reactions have ceased due to a lack of fuel, this became a major topic in 1930s. And then people suggested about small dense stars like white dwarf. Now we talked about this a lot, right? How white dwarf, what's the basic physics behind this, which is basically the electron degeneracy. Okay. Now, so this was in the year 1931 or so. Similarly, another development came in the year 1932 when we have possibility and physics discussion by Landau regarding the neutron stars. So just like the white dwarf, we have got a neutron star where you see the neutron degeneracy will be resisting against the gravitational collapse. But again, there are certain differences. Suppose I ask you, what are the differences between these two compact objects? Well, similarities I have discussed in this way. The degeneracy pressure is the similarity linking. What's the difference? Number one, look at the density of the two objects. They are very different. Similarly, size, very different. And what more? Different? I have already discussed about this in the class. Effect of general relativity is very little in the case of white dwarf, but it is not so in the case of neutron star. Yes. So general relativistic effects are also important. Now you see, around 1939, Robert Oppenheimer and collaborators, they actually showed that neutron stars like white dwarf, they have a maximum mass. So let me write it down. So around 1939. So neutron stars have maximum mass. Now I have skipped the part of the discussion about the white dwarfs having maximum mass, and that is the Chandrasekhar mass, right? Now I am just for the time being, I am not talking about it. We have discussed it in the class. I want to talk about black holes. Okay, so above that limit, they found nothing to prevent a star that has exhausted its nuclear fuel from undergoing a complete gravitational collapse. Now, using general relativity, they showed, Oppenheimer at that time, they showed that according to a distant observer, such a collapse would take an infinitely long time, and the process appearing to slow and freeze as the shrinking subject approached the Schwarzschild radius, even though the image would soon become dim and reddened. Just hear me out. Very soon I will show you the mathematics of this as well. Okay. However, they also found that according to the observer falling within the collapsing stellar surface, there would be no such slowing, only a finite time being required to reach the central singularity. So, passing within the Schwarzschild radius would be a natural point of such a fall, relatively uneventful for the falling observer, though actually marking a point of no return. Now this is what started slowly. So people started discussing about such compact objects known as black holes using general relativity, and that's how the real birth of this discussion on general relativistic black holes started. Okay, now afterwards we talk, now you see this all discussion is regarding the static black hole, but very soon Kerr, in 1963 he solved the metric solution, found the metric solution for solution for Einstein's for this rotating black hole. And we also later on, even after so long, much after later after that, we got experimental evidences about that. So basically, if we talk about black holes, we have got three basic possibilities. One is the simplest one, which is black hole having only mass m. Of course, it has got a size Rs, Schwarzschild radius, and this is known as the Schwarzschild black hole. Next one is black hole which is rotating, so mass m, angular momentum, and this is Kerr black hole. And after that we have got a third part as well, third type, which has a mass m and it has got a charge as well, and it is known as, you can say, charged black hole or Nordheim, another name, black hole as well. So three basic black holes. Now out of that we will be talking about this one today only. In your fourth semester, along with this, you will be talking about this as well. You will be learning about this. So let me now start with so till now I have talked about somewhat physics. Now let me talk in terms of mathematics. Okay. Now we will consider the gravitational field surrounding a very dense condensed mass concentration m with spherical symmetry. Okay. Now you see the vacuum solution of Einstein's field equations for this case was found in the year 1916, as I told you, by Schwarzschild, Kerr-Schwarzschild. Now this gives a line element ds, that is basically the distance between neighboring events in a four-dimensional space-time like this. Let me write it down completely. Okay, so this is my, you can say this is equation 1. Now note that here we have to sum from 0 to 3. Sum from 0 to 3 over indices I and j. and where the usual spherical coordinates r, theta, phi are taken as spatial coordinates. So usual spherical coordinates r, theta, phi, they have been taken as spherical coordinates x1, x2, x3, and x0 is equal to ct. You see this rs over here, this is a critical parameter, and this is basically the Schwarzschild radius rs, and this is given by 2 gm by c square. And so this has a value of 2.95 kilometer for m is equal to m solar for the sun. Now the second component of this metric tensor, you see here, this one, the second part, this becomes singular at r is equal to rs, but it can be shown that this is a non-physical singularity, disappearing when other suitable coordinates are used. This I have just talked to you before. Now, next I am going to introduce the proper time. You see what I am going to do? I am going to talk about this observer stuff. How is observer trying to interpret the physics? Right. So for that I have to first define certain quantities, which I am going to do now. So the first one is the proper time. Proper time tau. Now this is as measured by an observer carrying a standard clock and is related to the line element ds along his world line by d tau equal to 1 by c ds. Now this is equation 3. Okay, and this Schwarzschild radius expression, this was equation 2. There will be more to come. Okay, now you see, for stationary observer, this is proper time. So for stationary observer, that means dr is equal to d theta equal to d phi equal to what? Stationary, 0. Okay, at infinity. That means r tending to infinity. What will happen? This proper time tau is equal to, we call it like this, tau infinity. This coincides with t according to 1. This expression. This coincides with t. Now let us consider two stationary observers, one at r, theta, phi, and other at infinity. Okay, then what is the relation between the proper times of both of them? Well, the relation between the proper time between the two of them is this following: 1 minus rs by r to the power half. This is equation 4. Now suppose that the first of them operates a light source emitting signals at regular intervals d tau. Okay, light source intervals d tau. Say for example an atom emitting with a frequency, example atom emitting with a frequency nu0 equal to 1 by d tau. Then the other one receives the signals and measures the intervals in his own proper time as what? D of tau infinity. right? That is, he measures another frequency. So other measures what? His frequency is basically 1 by d tau infinity. Now the resulting redshift, okay, so the resulting redshift due to the gravitational field is what? Let me write it down. So let me write down the redshift. So it is basically nu 0 by nu minus 1. So this is d tau infinity by d tau minus 1, and this is just 1 minus rs by r to the power minus half minus 1, and this gives, which gives z tending to infinity at r tending to rs. Now this is equation 5. Now you see the metric components in the first equation. Here, where was it? Yes, the metric components in the first equation show that the four-dimensional space-time x0, x1, x2, x3 is basically curved, and this holds for the three-dimensional space, right? Now at the surface of a mass configuration, okay, so at the surface of a mass configuration of mass m and radius r, the Gaussian curvature, this is denoted by k, of position space. These are concepts, okay, and this can be written, you see, like this: gm by c square r cube. This you will also learn in your advanced relativity class, but let me just write it down for the time being, because this has got significance in what we are going to discuss. Now this is usually very small compared with the curvature, so small compared with the curvature what? R to the power minus 2 of 2D surface. Let me take an example. You see, this value is approximately, so minus k is of the order of 2 into 10 to the power minus 6 r to the power minus 2 at the surface of the sun. But this again has the value of 0.15 for a neutron star. Okay, so this means that the two curvatures are compatible at the surface of a black hole with r is equal to rs. Fine. Now what I am going to do is, let me talk a little bit about the geodesic. Again, I am going to talk very little. So let us consider a test particle small enough for the gravitational field not to be disturbed, which moves freely in a field from point A to point B. Now its world line is four-dimensional space, is then a what? Geodesic. So the length SAB is an extremum. So this means that any infinitesimal variation does not change the length. So let me write it down as SAB, which is defined as A to B ds is equal to 0. Now if the test particle moves locally with velocity v over a spatial distance d sigma, then the proper time interval d tau will be smaller the larger the v. So this means that we will have d tau is equal to ds is equal to 0 for v is equal to c. So this gives us, that means for photons or for other particles of zero rest mass, they move along null geodesics. Now for material particles, so let me write it down. That is, for photons or other particles of zero rest mass, they move along null geodesics. Now for material particles, the requirement, what's the requirement? This is the requirement, right, of special relativity. Basically this means that d tau square and ds square must be greater than 0. So such separations are basically known as timeline separations. Now world lines of material particles must be timelike. Okay, what about the other case? So other case, separations with ds square less than 0, or basically d tau square less than 0 would require, what would it require? Basically v is greater than c, and this is known as space-like separation. Okay, for example, the distance between two simultaneous events, that means dt is equal to 0, is space-like. Now you see the null geodesic the null geodesic ds square equal to 0, giving the propagation of photons, describe the hypercones in space-time which are called light cones. Now in order to also see their properties, so basically let me write it down, the null geodesics giving the propagation of photons describe hypercones in space-time which are called light cones. Now properties, let us discuss the properties of this light cone near r is equal to rs. So for that we will introduce a new time coordinate. এমন কিছুই আমরা করছি না, আমরা জাস্ট একটা কোঅর্ডিনেট থেকে অন্য কোঅর্ডিনেটটাই যাচ্ছি, so that we can better understand the physics. That's it, nothing else. All the maths is unnecessary, but this is important to understand the physics, and this is what we are going to do. So what's the new coordinate? Yes, let me write it down. The value of t. Yes, this is the one. So the new coordinate frame and the old coordinate frame, the relation. So this is equation 9, and as a result equation 1 becomes, so let me write down equation 1. What can it become? This is the result. Okay, so what do we gain? Number 1, you see, non-singular at r is equal to rs. Okay, understand? Now we consider only the radial boundaries of the light cones. That means, okay, let me write it down. We consider let me, before I say, so you see here, okay, observe this, non-singularity at r is equal to rs, but this 1 by r singularity is there, which is your gravitational singularity. You can never remove it by changing of the coordinate system, okay, coordinate frame. Okay, so we consider only the radial boundaries of the light cones. That is radial boundary manta ki, that is the path of radially means d theta equal to d phi equal to 0, radially emitted photons. Okay, then our equation 10, what will it give? For ds is equal to 0 will give, basically we see this equation. This is equation 11. Here we have just we did a division by c square dr square. Okay, now let me write down the solution. So solution, so just a second. So again let me write down this equation. So this is the equation, I am again writing it down. So the solution is this. This is the solution. Now you see, these derivatives are inclinations of the two radial boundaries of the light cone in an RT plane. These derivatives are inclinations of the, I will just show you the diagram so that you can better understand it. Just wait. Of the two radial boundaries of the light cone in RT plane. Let me show you. See here, this is what I have been showing you. So what we have shown you is the light cones at different distances. Different distance are from the central singularity. Now inside and outside. So this is inside your Schwarzschild radius and this is outside your Schwarzschild radius. Now you see, the first always corresponds to an inward motion with the same velocity. What I am talking about is this. Yes, so the two derivatives. Now see, as I have been telling you, these derivatives are inclinations of the two radial boundaries of the light cones in the RT prime plane. Fine. Now, this first derivative always corresponds to an inward motion with the same velocity c. The second derivative, basically, it changes sign at r is equal to rs here, being positive for r greater than equal to rs. So let me again write down this. The first derivative, it always corresponds to an inward motion with same velocity c. What about the second derivative? It changes sign at r is equal to rs, being positive for r greater than rs, where photons can be emitted outwards, dr greater than 0. Now you see, let me show you the expression here. So let me also write it down. Let me show this solution over here as well. Okay, so what happens is that with decreasing r, this second derivative, this becomes larger, so that the light cone here, you see, it becomes narrower. You see, it slowly starts becoming narrower and narrower. Okay, and its axis also turns to the left. You see, the axis is turning to the left. So, yes. So, axis turning to left, right? And also light cone narrows. So two things, not only the axis is turning to the left, but also the light cone is narrowing. Now at r is equal to rs, the light cone is such that no photon can be emitted to outside, dr is equal to 0. Now this is the reason for calling a configuration with r is equal to rs a black hole. Okay. And for speaking of the Schwarzschild radius rs as the radius of a black hole of mass m. Understand? Now for r less than rs in this region, here you see both solutions, both of them, they are negative, and the whole light cone is turned inwards. So here, in this case, both solutions are negative, right? And light cone, not only that, here also you see light cone turns inward, right? Therefore inside rs, all radiation together with all material particles which can move only inside the light cones is drawn towards the center, and this means that no static solution is possible inside rs, since it would, why? Because it will require a motion vertically upward in this figure, which is not possible, that is outside the light cone. Understand?